Let's look at a concept that I like to call the helpful force. Your book calls it the scalar or vector projection. And here's the idea behind it. Let's suppose I have an object, like this one here, and I want to move it horizontally along the floor to the right. So, in this direction. Now, to get it to move, obviously, I'm going to have to apply a force. So let's think about that. If I were to apply a force in the direction that I want the object to move, that would be a good thing. But let's suppose that I'm applying this force with a rope and it's really hard for me to pull right along the floor. So instead, I'm going to pull at an angle. Now, if we think about this, if I can pull with the same strength either directly along the floor or at this angle, which force would be most efficient in helping me to move this object along the floor? Let's take it to an extreme. Let's say I actually pulled straight up instead of at an angle. Well, clearly that wouldn't do me any good. I wouldn't be moving the object at all in the direction I wanted it to move. Now here, over on the left, this would be the most efficient. So what I want to know is how efficient or how much of my force is actually helping me in this in-between situation. Well, what I'm going to do is I'm going to break down my force, my directed force, into two components. The part that is going to help me by pushing along the floor, and then the part that's wasted. Now the sum of these two gives me my blue vector, or what I'm actually applying. So this piece right here is the piece I'm interested in. Now you've noticed I've drawn a right triangle here. So I can, if I know, let's call this vector A, if I know the information about vector A, how long it is, and what the angle is, I can figure out this unknown piece. Let's just call this P. Well, if I use my triangle trigonometry, I know that the cosine of theta is equal to P over the length of A. So that distance P, or my helpful force, is the length of A times the cosine of theta. Now if I wanted to be specific, at this point if I was saying that I wanted to move this along the floor in the horizontal direction, well, I would just add that vector information at the end and create a vector P that is this long and point it in the proper direction. So I take my 1 unit vector along the x-axis I, and I multiply that length times I to get my vector. So this first calculation here is my scalar projection, or helpful force. And then I take that length and I multiply it by a vector, in a unit vector in the appropriate direction. So that becomes my vector projection. Notice that if the angle between the direction I want to go and the vector that I'm creating, my force vector A, is more than 90 degrees, so if I actually had a vector where theta was greater than 90, the cosine of theta would be negative, and that would tell me that I'm actually working against my purposes, and I'd have a negative scalar projection and a vector that points in the opposite direction of the direction I was intending to move. So that's fine if we're working along the floor, but what happens when we're trying to move our object along a ramp Well, in that case, we still think about our directed force. It would be nice if I could pull directly along the ramp, but that's not the case here. Let's say I'm actually pulling at an angle off of the ramp. Well, I still want to create my right triangle, but only now my right triangle is going to be based on my direction, desired direction of motion. So it's going to, my helpful force is going to still point in the direction of the ramp. My angle is still theta. My vector is still the same. A is still my hypotenuse of my right triangle. So my vector projection then, my scalar projection or helpful force, is still the length of A times the cosine of theta. To point this length in the right direction, though, we need to know the original direction of the ramp. So let's call that vector, the ramp vector, B. If we take B and reduce it to a unit vector, then we have a direction vector in the appropriate direction for our force or our projection. So we remember that we take our vector and divide it by its length to get a unit vector in the direction of B. So now instead of along the floor, we have this unit vector in the direction of B. And to get our vector projection or helpful force, we would take that length that we've already calculated and multiply it by our unit vector, or B over the magnitude of B. So let's take an example of this. Here we have our B vector of 8I minus 5J plus 3K. And we can think of that as our ramp. That's the direction we want to move. And A is the force we're going to apply, and it's 10 units long at an angle of 70 degrees to B. So to find the vector projection, or the helpful force, we use our formula, which tells us that our vector projection is the length of A times the cosine of theta times the unit vector in the direction of B. So our length of A is 10. Then we multiply that by the cosine of 70 degrees. And then we multiply that by vector B, which is 8I minus 5J plus 3K, divided by the magnitude of B. And we get the magnitude of B by our super Pythagorean. So the magnitude of B is going to be the square root of 64 plus 25 plus 9, each of the components squared. So that's 89 plus 9, 98. So the square root of 98. And that creates my unit vector in the appropriate direction. So now we pull out our calculators and we calculate 10 cosine 70, and we divide that by the square root of 98, and we get this 0.3454. I'm going to store that to A to help me with some later calculations. And I'm going to multiply that by 8 to get my I component. So my I component is 2.764. I'm then going to multiply that number that we calculated by -5 to get my j component. And I'm going to multiply by 3 to get my k component. So my I component was 2.764i. Go back. My j component was -1.727. So minus 1.727j. And then my k component, 1.036. So this vector, p, is the amount of A that's actually pointed in the direction of B. Let's see if our answers match. And yes, they do. Let's take a look at these formulas, because we're not always given just the length of A and the cosine of the angle between them. You'll notice that our scalar projection here is awfully similar to the dot product formula of A and B that we just covered. A dot B is the length of A times the length of B times the cosine of theta. And our scalar projection is almost the same, it just doesn't have that length of B as part of the formula. So what I'm going to do is I'm going to introduce the length of B into the formula, but not affect the overall value, and divide by the length of B as well. And that simplifies because that numerator here is also the dot product. And if we have our information in component form, I can figure out my scalar projection without having to determine the angle between the two vectors. I can use this dot product formula instead. So now we have two ways to calculate our scalar projection. If I use that scalar projection and recognize that I take that scalar projection and multiply it by the appropriate unit vector to get my vector projection, well then I can take this formula here with the dot product and multiply by the unit vector in the direction of B, which, if we simplify, you can see turns out to look just like this. The dot product over the magnitude of B squared times the B vector. Let's see if these can help us in one of our problems. In this case, we have our two vectors A and B, but we have no information about the angle between them. We just have the components. So these revised formulas should help us. So A is -4i plus 5j plus 9k. B is 6i minus 8j plus k. So to find the scalar projection, we need to remember that the scalar projection now, our alternative formula for the scalar projection is the dot product over the magnitude of B. So our dot product, if we remember, is just the sum of the products of each component. So the product of the I components is -24 minus the product of the j components, which is -40, plus the product of the k components, which is 9. So we get -64 plus 9, which gives me -55. This -55 then needs to be divided by the magnitude of B. And the magnitude of B is going to be the square root of the sum of the squares of the components. So the square root of 36 plus 64 plus 1, which turns out to be 101 square rooted. So my scalar projection is going to be -55 over the square root of 101. Noticing that it's negative tells me that A is actually not pointed in the direction of B at all. It's actually an unhelpful force. Now to find the vector projection of A on B, we take our scalar projection and multiply it by the unit vector in the direction of B. So the unit vector in the direction of B is the vector B divided by its length. And we just figured out the length of B to be the square root of 101. So we get 6 over the square root of 101 I minus 8 over the square root of 101 j plus 1 over the square root of 101 k. And then we're going to take that value and find our vector projection. So we multiply that by the scalar projection value that we just calculated, negative 55 over the square root of 101. So we're going to get a vector whose denominators are all 101 because I'm distributing that square root of 101 across my vector. So all over 101, we have i's and j's and k's. And I multiply negative 55 times 6, which comes out to be negative 330. Oh, that's actually a positive 330. I multiply negative 8 times 55 and get negative 440. So minus 440 over 101j. And then I multiply 1 times negative 55. Actually, I have two negatives, so it's a positive 440j and a negative 330i and a negative 55 over 101k. So my scalar projection as we calculated was negative 55 over the square root of 101, and our vector projection, negative 330 over 101i plus 440 over 101j minus 55 over 101k. So let's recap. What is the symbol for a dot product? Well, it's simply a dot. What are the two ways to calculate dot products? Well, the first formula is here, the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. That's if we have information about lengths and angles. If we have the vector in component form, then we take the sum of the product of each component. So the sum of the I component product plus the Y component product plus the Z component product. What are the two other names for the dot product? Well, they're the scalar product and the inner product, mean the same thing as the dot product. What is the meaning of the vector projection of one vector upon another? Well, that's what I call the helpful force. It's the amount of the first vector that is pointing in the same direction as the second vector. What is the meaning of the scalar projection of one vector upon another? Well, that's simply the magnitude of that force that's pointing in the right direction. It's a single number and it's only the magnitude. How do we calculate the scalar projection quantity? Well, the way we calculate the scalar projection quantity is with this formula. The magnitude of A times the cosine of the angle between the two vectors. The formula for the vector projection is the magnitude of A times the cosine of the angle between them times a unit vector in the appropriate direction. Here we have two formulas. Here's the scalar projection, magnitude of A cosine theta, or A dot B over the magnitude of B. The vector projection takes that information and multiplies it by a unit vector in the appropriate direction. Or A dot B over the magnitude of B squared times the vector B. So we've covered both the initial formulas and the formulas for the scalar and vector projections that don't include the angle between the vector.